Okay, so let me start again. Hello, good morning, good evening, good afternoon, everybody, wherever it might be. It is my great pleasure to welcome Thomas Weber, who used to be from Torino and now he's from Bologna, so still northern Italy. And he will tell us about the infinitesimal braidings and Pre-Cartier by Bialgebras. Thomas, the floor is yours, the Zoom is yours. Take it away.
Thank you. Yeah, so I'm happy to be here. I'm glad to give a talk in this famous series of seminars. And I'm also happy to give this talk on site. So I would like to thank Piotr for making this possible. So I would tell you about my recent project here. That is recent work that I did with Artizzoni, Bottegoni, and Chandra. So the names listed here. Maybe some of them are also in the Zoom audience, I'm not sure. So if this is the case, they can help me out if there are challenging questions.
Andrea is online.
Very good. So I have one ally on Zoom. Great. Okay. So I will start by motivating a little bit what I'm going to tell you. So the motivating picture is the so-called category algebra correspondence. And this basically means if you have some additional operation on the side of categories, you will get some information on the algebra level and vice versa. So, okay, let's make this a little bit clearer. So if we start with an associative unital algebra H, let's say over a field K, then we can look at the category of left H modules that I write here as HM. And so here the objects are just left H modules and morphisms are left H linear maps, very clear. And so if we add now something on the level of modules, this will give us some extra information on the level of the algebra H and other way around. So let's see this. If we have even a monoidal category, so if we have a tensor product and a monoidal unit, then this tells us that on the algebra, we have actually a bi-algebra structure. So we have a co-product and a co-unit. If we have even more, so if we have a braidings, yes.
Don't you require some functor on this category?
So here there is a hidden functor. There's of course always the forgetful functor to simply vector spaces. But okay, here this is really just the motivating picture. I didn't want to be too complicated. But it's true, there's a hidden functor in the background. Okay, so if we have now even more, namely a braided monoidal category with a braiding operator sigma, this tells us that on the level of algebra, we have what is called a quasi-triangular bialgebra. Here we have an extra element R that is in the tensor product of H with H. That is called the universal R matrix. And we will see what are the axioms or properties of this R. And so this on the level of modules corresponds to a braiding that is a morphism that tells us how to flip objects. So what we did is adding something extra to this picture. Namely, we don't only have a sigma, but we have some extra operation T here. And we are going to see what this means. And then this guy here is what we call a Pre-Cartier category that will have this operation T, which on the level of algebra corresponds to an infinitesimal R matrix that is now this extra element chi, again in H tensor H, which on this side corresponds to the infinitesimal braiding, some operation T. And just to understand how the correspondence looks like, at least for the braiding and for the infinitesimal braiding. So if we have the operation R, then simply applying R and then using the tensor flip, this will give us the braiding. And for T, this will be simply the action of the element chi. Good, so this is just as motivation. So let's start with the actual talk. I apologize because some of the slides will be really basic. So I hope I don't offend the experts by now giving you the definition of a Hopf algebra, but we do it quickly. So just that we are all on the same level. So very briefly, what is a Hopf algebra? H a Hopf algebra is an algebra with multiplication mu, unit eta, and a co-algebra with a co-product here and a co-unit. And delta and epsilon have to be algebra morphisms. This then gives us a bi-algebra. And then for a Hopf algebra, we have also an antipode S. What does it mean to be a co-algebra? This is written in terms of these diagrams here. So if you read the diagram for delta, this is just a dual diagram of associativity of a product. And this is why this diagram is sometimes called co-associativity. While the second and third one, they just are the dual axioms of the unit. So in this picture, they're called the co-unit axioms. Furthermore, the antipode is defined, or the axiom of the antipode you can read in this diagram here. That might look a little bit complicated, but it just says that S is the convolution inverse of the identity map. Very well. We are going to use frequently.
In particular, we can conclude that the antipode is unique. This is one.
Exactly. So if there is one, there's only one. Yeah? But it might also happen that there is no antipode. Very good. So we frequently use Sweetler's notation to write the coproduct of an element H. So in principle, there's a finite sum here, but we are lazy, so we just write H1 and H2. And then in a similar way, if you have higher coproducts, so if you apply delta twice, so you end up in the triple tensor product, we will write H1, H2, H3, and so on.
I'm sorry, but I have to defend Paul Sweetler because the beauty of his notation is that he put parentheses over numbers so that you can distinguish it from subscripts. And you know that it has a different treatment. So
this is true. So this is even the more modern version where people get more and more lazy and don't even write the brackets anymore.
Yeah, but this can very easily be very confusing.
Absolutely. So if you don't specify this, like in the first section, people might get lost. Yeah, it's yeah. Anyway, so this is the most, or the latest version of this Sweetler notation. Okay, so again, very basic. This is from a talk I gave earlier this year on the Baby Steps conference that was for. So the message there was that Hopf algebras are everywhere and exactly, so that many people use them all the time, and so this slide is just so that hopefully everybody can find some algebra that he or she is working with all the time. So telling us that Hopf algebras are really everywhere and we are all using them, even if we don't know it. The first example, of course, is the group algebra for any group G. Then you have a coproduct simply as this called so-called group-like coproduct, and the antipode really being the inverse of the element G. And then you simply extend everything in a k-linear way. Second example is that of the universal enveloping algebra of a Lie algebra with the primitive coproduct for an element in X and the antipode being minus the element. And then you extend the first two maps as algebra maps and the antipode as an anti-algebra map. Third example are regular functions on an algebraic group. And this one is really the dual example to one. So here, the coproduct of a function f is given by the product on G. The co-unit is given by the unit on G, and the antipode on f at a element G is just f of the inverse of this element.
So in particular, all finite group signs.
Absolutely, yes. And yeah, just note that what is crucial here, we use that the tensor product of the regular functions is isomorphic to the regular functions on G cross G. This is the
essence of regularity of functions.
Yes. Yeah. Very well. Okay, so those examples are, let's say, rather classical. Let's have some example that's a little bit quantum. So this is what is sometimes called Sweetler's Hopf algebra. It's generated by 1, G, and X, such that G squares to 1, X squares to 0, and xg equals minus gx. So we have a 4-dimensional vector space with coproduct of G simply being the group-like one, of X being a primitive one with a slight twist here with G.
So it's called skew primitive.
Skew primitive.
Skew primitive.
Skew primitive. Okay. Thank you. And okay, you can figure out that those are the right antipodes to take. Very well. And the last example is actually a class of examples that people like very much, and these are Q deformations of matrix groups called GLQN or SLQN. For example, let's understand SLQ2. This is the free algebra generated by some alpha, beta, gamma, delta modulo these Manin relations here, which is mainly a Q commutativity. Not always. I mean, beta and gamma like each other. Alpha and delta really hate each other. And there's a quantum determinant relation also here. So this one becomes a bi-algebra using this matrix co-multiplication that's written here. And I didn't even write the antipode because we don't really need it here.
Please correct me if I'm wrong, but I believe that in the Sweden's-Scope algebra, S squared is identity, right?
Yes.
It's
finite dimension.
But it doesn't mean that S squared is identity. It's
So in finite dimension, the antipode is invertible, but
it's invertible. There's nothing S
yeah.
squared in it. It's a completely different cup of tea. But by far, it's a totally different issue.
yes.
I mean, you have the famous Radford theorem for the fourth power of the antipode. So it's absolutely not identity. But this example is identity. So if you want, one of the biggest pleasures derived out of, for example, I guess SLQ2 and GLQ2, GLQN, whatever it was, that the square of the antipode is now nice non-trivial automorphism. We are no longer Katz algebras.
Very good. Okay.
This was a breakthrough because people knew such examples ages before quantum groups came into being in Berkeley in 1986. So the big essence was, hey, S squared identity is a wrong assumption.
Right. You don't always have it. Yeah, absolutely not.
In natural examples.
Is there an example of 4-dimensional Hopf algebra with antipode is not?
I don't know if it's 4-dimensional.
4-dimensional.
I don't know if 4-dimensional. No. This I don't know, but
I cannot tell.
That's not a question you can answer now.
But we can look it up, like let's say low dimensional Hopf algebras. I think there should be lists of them. So
the question for Google.
Yes.
For AI.
Yes, for AI, yes. ChatGPT.
Okay, so this was just to set the stage to understand what is a Hopf algebra. The next ingredient that we need is that of a braided monoidal category. Also here, I will be very brief just to give you the idea. So we take a category C with a monoidal structure. So something that we think of as the tensor product. It has all the nice properties we know from the tensor product of vector spaces. And for this one now, we also want a natural isomorphism, sigma, that maps the tensor product of two objects into the flip of this one. And so this sigma has to satisfy some axioms that I wrote here in a diagrammatic form that we have to read like this. So the braiding is written as a crossing, and we read the diagrams from top to bottom. So what the first one tells you is that if I braid M with N tensor O, this should be the same thing as first braiding M, and then braiding M and O. And the similar thing happens when the tensor product is in the first entry. So you are braiding M tensor N with O by first braiding N and O, and then M and O. Let me also say that for me, I will always work in strict monoidal setting because I don't want to worry about, associata, so how to re-bracket. You can include this in the picture, but it's just getting a bit messy. And I think for the purpose of keeping this talk simple, I work in the strict setting. Otherwise, I can also always strictify.
Yeah.
Very well. So if those axioms hold, I call C a braided monoidal category. And you can show that in this case, the braid relations hold. And those are written here. And this just means that braiding the first two, last two, first two is the same as braiding last two, first two, last two. Very natural definitions here. Okay, so on the first slide, I had this category algebra picture. So this is, of course, on the side of category theory. Let's see what is the algebraic notion corresponding to braided monoidal categories. And this is a quasi-triangular Bialgebra with a universal R matrix. So if we start, let's say, only with a Bialgebra with coproduct delta and co-unit epsilon, you can show that the category of left H modules that we have written like this is monoidal. So what we do is we take the tensor product vector space, and then I just have to tell you how to left act on this tensor product. And this is done exactly using the coproduct. And you can see that this is a left action because delta is an algebra morphism. And in a similar way, you can act on the monoidal unit, which is just your ground field K, by using the co-unit, which is also an algebra morphism. So you can see this is a left action. And there's a theorem proven in the early 90s that says that so if you have an algebra H, then your category of left H modules is braided if and only if H is quasi-triangular. What does this mean? This means that we have an element R that is, first of all, invertible, and furthermore satisfies 1, 2, 3 axioms that we are going to read in a second. If we have this element, we can show that the braiding can always be written in this way. It's just acting with R and then flipping everything. This is why it's written here, R up on the flip. So, okay, so let's read the axioms, starting with the last one. This one here just tells us that the sigma is a morphism in the category of left module, so that it's left linear. It's exactly what you need here, where delta op means this is the opposite coproduct. So using the coproduct and then flipping. And axioms 1 and 2, they will correspond to what is written here. So to those two axioms, sigma has to satisfy. So let's read them. So here, the first one means that if I apply the coproduct to the first tensor entry of R, something happens. So first of all, I end in the triple tensor product. So H, tensor H, tensor H. What I have on the right side is like 2 copies of R, where now this R2, 3 means this is just one tensor R. And R1, 3 means that there's the first tensor leg of R is in position 1. The second one in the third, and in the middle I have a 1. Yeah. And in a similar way for the second axiom here, just saying if I use the coproduct on the second tensor leg, I get 2 copies of R in this way. Okay, this is what a quasi-triangular Bialgebra is. Short note, so sigma is a symmetry, meaning that it squares to the identity if and only if R is triangular. So this means that the inverse of R is the tensor flipped R. So this is a subclass of quasi-triangular Bialgebras that is also interesting, but here we are working in the more general setting. So just mentioning that.
Just a very naive question, if I may. Can you somehow literally interpret this adjective triangular? So do you have some presentation as a matrix that is very triangular?
That's a good question. And I think this is the case at least for the classical counterpart, right? So there's this classical R matrix, yeah. But I'm the wrong person to ask this. Someone more qualified could easily answer it, but it's not me.
Okay.
Okay. Okay, let's have a look at some examples. So first of all, every co-commutative Bialgebra, meaning that the coproduct equals the opposite coproduct, is triangular, using R simply as 1 tensor 1. So you can see if delta equals delta op, here I can take R as 1 tensor 1, and also the first and second axiom are trivially satisfied. So this happens for the group algebra case or for the universal enveloping algebra of a Lie algebra.
So you're trying to convince us that one is inverted.
I do. I hope everybody is on board with this assumption. And okay, so here the corresponding grading on the level of modules is, as you can see, simply the tensor flip. So this means that for those cases, nothing really interesting happens. Everything is just using the tensor flip now. So let's try to see something more interesting. And this happens for the group algebra of the cyclic group. So for Zn, you have a special R matrix, which is written here. So this G is the element such that G to the power n equals 1. And you can show that this gives you a quasi-triangular structure for this group algebra. Let's focus for a second on the case n equal 2. And in this case, this gives you what is sometimes called a super geometry braiding. So this means on the level of modules of Z2 modules, this is exactly the sign rule that you get by flipping two graded elements. Yeah. So in this sense, you can understand local super geometry as graded geometry.
So is there any reason for this minus? I mean, you are basically going over the roots of unity. What would happen if it's the e2 minus 2 pi I blah blah blah? You would have e to 2 pi I blah.
So this formula I took from Majid, and I would say there's a minus. So I hope there's a good reason for it, but I cannot justify it.
Can anybody see that?
It is irrelevant. So you can take the complex conjugation and
That's what I think. This is why I don't understand why I put it there.
Yes. Maybe it's also not there, and I just included it by accident. Sorry, I will check it.
Okay, because sums are usually additive, so just renumbering.
True.
But there is this word supergeometry, so maybe it has something to do with the physics. And in physics, usually people are stick to some particular convention. So maybe
it's like choosing this Q inverse work as well.
Yeah, exactly.
yeah, but for example, in quantum mechanics, when people consider the Schrödinger evolution, they usually put minus in this exponent. So maybe
Yeah, but there's a reason
something
for
in
it.
this spirit.
But here we have an identical mathematical formula. It's not a question of some choice of a convention. It's just identical formula. So why bother with the minus?
I see. Okay.
And this expression is also has some hidden symmetries. For instance, if you change this J by minus J and K by minus K, you obtain the same. You cannot change the sign of this.
Exactly.
Yes. I don't know. So I will check this. Maybe this minus entered there by
The
accident.
direction of a discrete time even doesn't help. You know?
Yeah.
By the way, coming back to this Swidler example,
Yeah.
it is the smallest
Uh-huh.
Hopf algebra whose antipode is not involutive.
So not involved. Wait a second.
S squared is not identical.
So please come back.
And this is the smallest example.
Okay. So fine. So how about the formulas?
Okay, so S
Identity on G,
Yes.
and if you apply S squared to X, so I have S of minus GX will be minus S of G, which is again minus G, S of X, which is minus GX.
Right.
Minus G times minus G is G squared. G squared is 1, so I don't see where you have.
So it is strange because it is regarded to be the counterexample to involutivity. So maybe
Surely not by this formula.
okay, so maybe there is
That's why I
maybe there is something wrong with this formula.
a good question. So
That's why I asked this question, because I expected it not to be involved. I wasn't sure why it should be involved, but I did the calculation and it is involved according to this formula.
yes, I would say so.
And I don't see anything wrong with this. Elmar, yes?
Isn't it the twice minus sign, and then you get a minus sign from commuting x and g? So this minus identity is squared on x is minus x, isn't it?
S of,
No.
yeah. So S of G is G inverse.
But
Yes,
Yeah.
G inverse is G.
The same.
Yeah.
So no.
But on x, twice on x, you get twice a minus sign, but then you commute g and x, and you get another minus sign, so you get minus.
S
So here I made
is
this
minus
mistake.
G.
Oh,
Minus G.
Okay, Elmar, thank you so much. It was my mistake in my calculation.
Minus.
Yes,
Survive.
yes, because I commuted it in my mind, whereas it does not commute. Okay,
Right.
thank you, Elmar.
Anti-commute.
Okay, so you're right. So that's this is already not involved. Okay,
It's very complicated to do these simple computations in front of an audience. I am absolutely not.
I'm talking about the dimension of this. This is the small
Yeah.
example.
but so the discussion was worthwhile. Yeah,
Yeah.
I mean, we
Also
the smallest dimensional Hopf algebra with a non-involutive algebra. Brilliant. I'm happy.
Okay. Ratings, quasi triangular, and we've got the examples. Right, and now the last example I want to mention is the Drinfeld double of a finite dimensional Hopf algebra H. So the Drinfeld double is just this tensor product of the dual of H with H. And this has a natural quasi-triangular structure written here, where the E lower I is a basis of H and E upper I is the dual basis.
Sorry, you sum over this.
Yeah, sure. That's sum over.
That's the Einstein convention.
Einstein convention. Yeah.
Yes, absolutely. Okay, so here is now the first new thing.
I have a historical question. I'm sorry, I cannot resist it.
Sure.
I just met Einstein at Frankfurt Airport. Is there any reason why Einstein's statue would be at Frankfurt Airport? Was Einstein somehow, you guys are from Germany. Is there any reason why somehow Frankfurt will boast a statue of Einstein at the airport?
I have no
Maybe
idea.
she took a plane from Frankfurt to Princeton.
I would associate him with Göttingen or yeah, it's like, then any reason why Einstein should stand for Frankfurt?
Was there some
No, just for sitting with E equals MC squared, you know, his
no comment?
no comment, his lifetime statue, life-size statue, yes. Sitting on a bench next to passengers. E equals MC squared. I was wondering, I understand the statue of Hilbert in Göttingen, you know, Hilbert Raum, it's really fantastic.
And Adorno in front.
Yeah.
Of course, I don't know, but I would guess that there's a justification. So probably
But you don't, if you being German don't know it,
it means nothing. Yeah, so I wouldn't take us as the
benchmark.
Sorry for
the interruption.
Okay, so now the first new part, let's say. So this is really coming from my early background. So I'm coming from deformation quantization. So if I
Background radiation.
exactly. So, and if I see something, I'm always thinking of, okay, let's do formal power series and look at what happens in low orders. Yeah? So I did the same thing here, starting with a Bialgebra H. Let's take the formal power series in some formal parameter H bar. And then this is a topological Bialgebra with the H bar linearly extended algebra and co-algebra structures. So here, this just means that you have to be a little bit careful when it comes to tensor products. So here you have to take the completed tensor product in the H-baric topology.
Yeah,
that's basically everything. Yeah. Okay, so we have a topological Bialgebra, and let's say we have an R matrix on formal power series. Yeah. So what happens in low orders? You can see that in zero order, you get a quasi-triangular structure for H. I mean, it's just reading all the axioms of R tilde in zero order, nothing new. This also means that R is an invertible element. So you can factor out R in this way here and write R tilde as R times 1 tensor 1 plus something in H bar plus higher orders. And then what we were asking is, what are the properties of this chi? So it's a very natural question, simply reading the properties. And this motivated the following definition that now works independently of formal power series. It was just to motivate the following definition. And it's like this. So we call a triple HR chi a pre-Cartier bialgebra with infinitesimal R matrix chi, that is an element of H tensor H, if, first of all, HR is a quasi-triangular bialgebra, and then chi satisfies some properties. And those are written here. First, I have a commutativity of chi with the coproduct.
You mean with the image of the coproduct?
With the image of the coproduct, yes. Mm-hmm. And
so wait, because this is a bit subtle. So do you really mean like centralizing, or do you mean with every single element?
Every single element, yeah.
Separately. Okay.
I could write this on an element, and this should hold for every element.
Exactly. I was incorrect. So it's not the image, I mean every element of the image, because it might happen that you have to change an element.
Yes.
So this is
absolutely. So it's not this. It's not with the image here. This is really meant element-wise.
Element-wise.
I was just too lazy to write it elements. So
the notation is correct. Right? Just was...
very good. And then two extra properties that I mean, you can guess that what was happening for R is that something happened when you apply the coproduct to one of the tensor legs. And here for chi, we see that we get two terms. And there's always a second one that involves also R and R minus 1.
That looks pretty symmetric.
Yes. And so this will be the main object to look at in the rest of this talk. Yeah.
So I have a question. Please assume that the original R, not R tilde, is identities 1 tensor 1. Okay. What is the interpretation of this?
We're going to see this, but I can give it an answer now. So okay. If this, so in case R is 1 tensor 1, what's written here is that chi is an element of primitive tensor primitive. You see that what's written here is just saying that both tensor legs are primitive elements. So you could interpret this as some braided primitivity if you want, yeah? But I mean, up to you.
But if R identity, it means simply that identity tensor delta makes it what?
So
chi 1 2 plus chi 1 3.
This means that here the second tensor leg of chi is primitive, yeah? Because you have this second tensor leg, the 1 plus 1 tensor this element, so it's really just primitivity.
Both legs are primitive.
Yeah, because of the
in the case R is 1 tensor.
Okay, but it's very nice to see that there's a deformation of primitivity.
Exactly.
By primitivity.
So yeah, it's a
yes, I know. By
primitivity. Yes. Two primitive legs.
Exactly. And okay,
like a duck.
With a duck. Sometimes we even ask more. We could also ask that R chi equals chi of R. If this happens, we call the triple Cartier, not pre.
So, we can also, okay.
And I'm going to motivate a little bit.
Yeah, so if R is identity, it means that chi is equal to chi of.
Symmetric in this case, yes.
It's symmetric. So it is two primitive legs and
symmetric.
And what's the meaning of this symmetry?
So a symmetric element that is built out of primitives. Yeah, so that's it. We are going to see this
an example
on the next slide. I mean, this is some special cases that I'm going to treat, and one is the one you just mentioned.
And is it really due to Pre-Cartier?
Part of it. So this last part, in case of a symmetric braiding. So in this case, it was not clear if you should take R minus 1 or R off, for example. But okay, we clarified that from this example, it's quite natural that this is the correct.
So does it mean that if R is identity, then this symmetric chi leads you to maybe not to the flip, but to the symmetric monoidal category?
You're talking about R tilde now?
Yes.
Oh, this is a super difficult question, and this will actually part of the last slide. I'm going to ask this question. So here we saw how to go from R tilde to chi. So now if you have R and a first order deformation of chi, there's a natural deformation problem saying, can we find R tilde? It's a very hard question. Or, I mean, I cannot answer, and I think it might be hard. Okay, but let's continue. So this was the definition. Okay, let's first have a look at the categorical counterpart. So what is happening on the level of modules? And there's this short proposition you can show that so you have a pre-Cartier bialgebra if and only if on the category of left modules is braided monoidal with an extra natural transformation T like this, satisfying two axioms. And so again, I mean, we can read them. It just means that if I insert a tensor product in one of the entries, I get like two copies of T, one with the two braidings on both sides. This you can try to interpret as some braided Leibniz rule. We are going to see later why this makes sense to call this a braided Leibniz rule, but okay. So this is a proposition saying that on the level of modules, chi corresponds to this operation T, natural transformation. And if we have a Cartier bialgebra, if also R chi is chi of R, then sigma and T commute. This is the meaning of this algebraic formula on the level of modules.
But wait a second. TMN goes from MN to MN. But sigma flips it.
Yeah, therefore.
So I'm a bit. Okay. Yeah, I noticed the TNM. Okay, but wait a second. So because it's categorical, so you have it for everything. Okay. I'm home. Thank you.
Very good. I said nothing, but
wait. Yes, there is a question in chat. It's okay. Einstein in Frankfurt was a part of Made in Germany marketing campaign. Okay. Wow. So special relativity made in Germany. You should buy it.
Yes, I bought it.
And export.
Okay, and then reading from the left modules, we can, I mean, there's a natural guess. What is the definition of a pre-Cartier category in general? So not only for left modules, but if you just take any braided monoidal category, you call it a pre-Cartier category if you have a natural transformation T satisfying those properties. And in this case, we call T an infinitesimal braiding. And again, it's Cartier if this extra commutativity axiom holds.
I have a question.
Yes.
So if you are considering this tensor category, let's assume that this has this forgetful functor to vector spaces. Then you can replace the field by formal series. And then you could consider this new monoidal structure with the tensor product over this power series. Okay. What the meaning of this with respect to this?
So I think you can understand this as a first order deformation.
Deformation of
your braiding, yeah.
Monoidal structure of this. Okay.
Yes, I would say this is the interpretation.
As expected. Okay. Thank you.
Okay, and so this is the comment that part of this definition was known in the literature, namely when sigma is a symmetry, so when it's squaring to 1, and you have this extra commutativity of sigma and T, this gives back the known notion of a Cartier category that was first introduced in this paper in 1993. You can also find it in a chapter in Kassel, and more recently it appeared in this paper of Heckenberger and Wentham. Here, our definition is of course more general, since we work in any braided monoidal category and we don't ask this extra. And we're actually going to see that in some very natural cases, you cannot ask this extra property. It's asking a bit much.
So the context of this Cartier category is the context of the classical representation theory of like enveloping universal algebra.
The most prominent cases that were looked at are really universal enveloping algebra, in which case R is just 1 times 1 and the braiding the flip. This is what those people used.
But still this T could be non-trivial, even in this case.
Yes. And in this case, as we are going to see, this T will correspond to some primitive element. Yeah, so primitive tensor primitive. Yeah. Okay. Good. So now let's see some examples. The first one is the trivial one. That is, of course, trivial, but always good to have. So it says that you can see from the definitions that the infinitesimal R matrices form a vector space. So you can scale them, which also means that chi equal 0 always works. So every quasi-triangular bialgebra is a Cartier bialgebra if you take chi equals 0. So if you go to the definition, you can see that chi equals 0. Back. Chi equal 0 works. And if you have one chi, you can always scale it and it still works. Okay, so was the trivial example. Next, something non-trivial. That is the case of a quasi-triangular Lie bialgebra. So this is a triple G bracket R, where G bracket is just a Lie algebra, and this R is an element in the Lie algebra, tensor Lie algebra, that is ad invariant. Just put in what it means, yeah. And it satisfies the classical Yang-Baxter equation that was written here. And in this case, you can show that the symmetrization of R gives you an infinitesimal R matrix for the Hopf algebra UG with R matrix 1 times 1. And this is, as you mentioned, the thing that Kassel, for example, and others were looking at.
So this example is a source of considering this symmetrized or symmetric chi's.
Yes, exactly. And for example, this is then, so quantizing those guys will lead you to the Drinfeld-Jimbo quantum groups. Yeah, so this is really in the proof, you use this formula. Okay. The next example, let's say that the classical case, if you have commutativity, as we have seen, this will correspond to primitive elements. So H is commutative. It follows that chi has to be in primitive tensor primitive. And it's furthermore Cartier if and only if chi is symmetric in that sense. Yeah. So this also means that in some cases you cannot have something very interesting. If you take an abelian group and you have a look at the group algebra, since you know that there you don't have any primitive elements, it of course follows that the only possible chi is the trivial one. So in this case, yeah, you cannot say much. And we are going to see that you get more interesting chi's the more quantum you are, kind of. So this is really something that happens in the quantum realm and not so much classically.
Sorry, why? What about non-abelian but finite groups?
So if you are non-abelian, then of course you can have commutative.
Yes, but what about this?
And then okay, you can still take R as 1 tensor 1 because you are co-commutative, and then it still means that your chi has to be in primitive tensor primitive. Yeah. And
but what are primitives of kg when G is finite?
Those are elements such that if you apply the co-product, it's the element tensor 1.
We know
you can have
such. Okay, you have such example.
Yeah. For instance, in the Swidler topology, it's finite dimensional. Okay.
But
now I get it.
But it's not of kg form.
Yes.
So wait, because I'm now confused. So is it a reason or this particular conclusion that chi's go to 0 that G is abelian, or that G is or that this algebra is always co-commutative?
Yeah, so the point is that here we don't have primitives, and in some cases, for example, in the abelian case, but so you're saying for the group algebra, we always know that since it's co-commutative, we can take R as 1 tensor 1, So in this case, the definition means that X has to be primitive. Okay, so actually this is not even needed. So
Yeah. So
Because I was-
okay. So I wanted to fit it in this commutative part here, but okay, I could have done it as a separate example. And
I think it's worthwhile to,
okay,
because it's misleading. I mean, you think
a bit.
it's a billion, but no, it's
Yeah.
for commutative. And the
Right.
quantum group is a billion. This is
Right. This is not needed here. Okay. Very well. So let's see how I'm doing with time. So like half over.
5 minutes, yes.
Okay, very good. And I'm okay, not halfway through, but let's see.
Yeah, 10 out of 27, yes.
Good.
so I was exactly.
Good. So let's go back to Sweetler's Hopf algebra. And for this one, we classified all possible chi's. So, okay, we know this is how Sweetler's Hopf algebra looks like. It is known that all quasi-triangular structures on H, they are actually triangular, and all of them are of this form here with some scaling factor lambda. And so those are all possible R matrices on Sweetler's Hopf algebra. And for those, we classified all possible infinitesimal R matrices, and they're all of this form and work for each of the R lambdas. Also here, alpha is just a scaling factor. Okay, this is a computation. You can show that this is the only possible.
And,
So
and
if
how about
symmetric, it's
exactly, because it's very asymmetric. What if I put, I don't know, X tensor GX, for instance?
X tensor GX doesn't work. No. So this will not.
an exhaustive one parameter family.
Yeah, I know, but I'm surprised
So
by the symmetry.
if alpha is non-zero, this cannot be symmetric.
Right, and this is like this, the last part here.
Yeah.
So we have this R chi equals chi of R only for the trivial chi. Yeah.
Yeah, but I say I don't want Cartier. Okay, I'm happy with Pre-Cartier.
Mhm.
And when I'm still
You
surprised, like the exotic
Mhm.
one parameter family is given in such an asymmetric form. That was my point. I don't care about Cartier.
Mhm.
Just how about Pre-Cartier? What is the reason behind this asymmetry?
the reason is that also your coproduct, for example, is not symmetric.
Okay, that's a good answer.
G.
Okay, yeah, thank you. Yes. Yeah.
This last part here also tells us that having this more general definition is quite natural, because even for those simple examples, we see that if we want something non-trivial, we need to relax the definition. Okay. Just mentioning, there's a work in progress of the PhD students that show that this even works for all the Redford Hopf algebras, En. So here, those are Hopf algebras with generators G and X1 up to Xn. When you said E1, you get back Sweetler's Hopf algebra, but here, yeah, you can have more complicated Hopf algebras, and also for those, they classified all possible infinitesimal R matrices. That's something we're going to see soon. And okay, later we will see many more non-trivial examples via some modified FRT theorem. So, but okay, I'm building up. This will be one of the main part of the talk, hopefully. Let's see if I can make it there. Yeah, just some theorem. Maybe the first interesting thing that we showed in this setting is that somehow Hochschild cohomology enters. And it's in this way. So you take a pre-Cartier quasi-triangular Bialgebras. You can show that chi is automatically a Hochschild 2 cocycle, meaning that this equation here is satisfied. And furthermore, it follows that chi satisfies what we call the infinitesimal quantum Bialgebras equation that looks a bit horrible, but it's actually not that complicated. It's every term you can see has 3 R's and 1 chi, and you are simply shifting chi through all of the formulas. That's it. Huh? Okay.
And may I ask you what is the Hochschild complex here in which you have this 2 cocycle?
Yes, so for this you need the Hochschild differential, of course, yeah. And
Yes, of course.
I wrote it for the one cochains here.
Ah, you wrote it here.
But only for the one cochains. For the two cochains, it's basically you have to put this on the other side.
But you just take the powers of your Hopf algebra as your.
Yes, exactly. So it's powers of the Hopf algebra, right?
And when you construct all these Hochschild boundaries, right, differentials using coproduct. Okay, I'm home.
The usual
Okay.
simplification.
Yeah. Just wanted to make sure.
Okay, a comment that part of this, at least for the first one, this Hochschild part, was known for the case of the universal enveloping algebra with R matrix 1 tensor 1 and the chi coming from a quasi-triangular Lie algebra. There, Sean showed that if you take this symmetrized R, you get the Hochschild co-cycle. But here we are, of course, in the most general setting, and this still works.
So what is the homological interpretation of this symmetrization?
Again, it should tell us something about the obstructions, maybe if I can extend this first order deformation. But it's
in the deformation theory, it is the following well-known fact that if you have this Hochschild co-cycle corresponding to the first deformation of the product, then you can split it into this symmetric and anti-symmetric part. And this symmetric part can be killed by some co-boundary. Okay, so I wonder, is it so in this case that you can kill this anti-symmetric part by some co-boundary?
That in this case, we could even show that what you get is actually a co-boundary. Yeah. While in the general case, it will not be. So here, there are honest co-cycles. Yeah.
Yeah. So this symmetrization in general.
We don't do it. So this is just what's happening here for this UG case.
In this example, it works.
Yeah. But in general, I'm not sure. Probably not. I would be.
Probably not.
Yeah. Okay, but we can say something about co-boundaries. This is what's happening next. And for this, we need actually a Hopf algebra. So we also need an antipode. In this case, when we write chi as a finite sum in this way, so the chi I tensor chi I, then we apply the antipode to the first tensor factor, and then we multiply. So we get an element of H, and we call this element gamma. One thing that you can show is that gamma is automatically central. So okay, that's the way to get a central element. Interesting. And we call this the Casimir element. And this plays a role in the next proposition.
Sorry, what is the relation with Casimir elements provided this enveloping algebra?
Okay, I can tell you. So if you are in this example of universal enveloping algebra, and you take the corresponding, and you have a complex semi-simple Lie algebra, you take the corresponding Casimir element, and this will lead to the same chi in this way using this formula.
I have a trivial question. Here you use these upper and lower indices, but unlike for a dual basis, these are actually the same things. Chi upper I, superscript I, and subscript are the same. Yes.
No, so here it's really a finite sum. So chi is in H tensor H. So I want to see it as a finite sum here of
this is just labeling first like second like.
In a sense, they are not orthogonal.
No. So this is like meant as a dual basis or something. No. It's really.
It's like even if you have something which looks like orthogonal, then you have some basis, and the basis in the dual. And then taking the scalar product, you can identify it with the original space, and then you obtain chi I lower and chi I upper, which doesn't necessarily coincide.
Yeah, so here's really just a way to identify first and second.
Yeah, because you can surely choose chi-i's to be linearly dependent, right?
Yes.
So if you have a finite
Chi upper I are
space, you can do that, yeah. It's just here, I mean, this could also be an infinite dimensional algebra. We don't mind. Okay, so then coming to this second proposition, or not this proposition here, that says, okay, if we are now in the Cartier triangular Hopf case, so a lot of assumptions, yeah, then we can show that chi is not only a co-cycle, but even a co-boundary. And it's in the, so it's the image of the Casimir element under the Hochschild differential V1 that is written here. So this also tells us that the
so it is so that the symmetric part.
So I don't see where there's
it should be not symmetric, yeah.
But it's using a lot of assumptions in the sense that, for example, we couldn't show this in the quasi-triangular. We have to go to the triangular and Cartier. And okay, we need Hopf in order to write down chi. As
of course, one is symmetric only if delta is co-commutative.
Yes.
Yeah.
Yes.
Yes, and then we could show that in this case we get a co-boundary, but in general, without any assumptions, you always get a co-cycle.
Yeah. So expecting this chi be symmetric when the delta is not co-commutative is not natural. Right?
I mean, we don't have to. We could still show it, yeah, but
but why should you expect that chi is co-boundary in general? It's not in general. It's under these assumptions.
no, it's not.
Yeah, but if in this cohomologically trivial case, it is.
So here
The boundary is not symmetric, so why to expect that something is
So here it's
symmetric?
definitely.
By the co-cycle should be symmetric if co-boundaries are not symmetric. Yeah.
But yeah, this was only this very special case where it was, and our case is not. Okay, good. So maybe because time is a bit short, I will skip this slide. It's just a way to get other examples by, for example, using a Bialgebras map, or you can tensorize and you can twist things, and you can still get examples of pre-Cartier Bialgebras, but this one I will skip because time reasons. I think I also skip or just go very briefly over these co-modules. So what's happening now is we did the story for modules, and the corresponding algebra structure was quasi-triangular Bialgebras. For if you would rather like to work with co-modules than modules, you will have something that's called a co-quasi-triangular Bialgebra. So everything gets a co, and just giving you this story briefly. Take a Hopf algebra, actually a co-algebra would be fine for the moment, but whatever. Wow,
Too much.
like this.
A little bit bigger. You can use this. No. Percent.
Yes. But now it's too big.
Too big.
Use the keyboard. If you use the keyboard, it will go back.
So
Just arrows.
To what?
Arrows.
Arrows. No. Still too big.
I can try to.
Yeah. So a little bit. Yeah.
You tell me.
That was 375. No.
Yes.
Okay.
No, that's too small. No, it's not the whole. 375.
But it was
No,
at some moment.
375. More. But it should be somehow.
Yeah. No. Too much.
No.
Yes.
Wait, something.
It's okay. It's okay. Yeah. A little bit too much.
That's fine.
There's a lower bar of your screen with
Yeah.
Thomas Weber, Infinitesimal, Braidings, and
Okay. Maybe it should be, yeah, but it's so annoying that I cannot change it.
It's the
Okay. But it always would go back to the default if I use the keyboard.
Yeah, probably I messed up something. I'm sorry.
The size is the same.
Not that.
Okay. So let's see, half an hour or so.
Yeah, half an hour exactly.
Let's see. Okay, so maybe I can also go through this slide very quickly. I guess all of you know what a co-module is. It's just a dual notion of a module. You have a coaction rather than an
I don't know what a contra module is.
So very fine. Then I don't. So I only specify maybe the way to write it. So for the coaction on an element M, I now don't write M1, M2, but M0, M1. And here the 0 tells me this is the part in M, and 1 tells me this is the part in H. So if I coact twice, I will get something that now I will write as M0, 1, 2. 0 always tells me what is the part in M, and the positive ones tell me what are the components in H. And if I have a left comodule with H now on the left, I'm going to write this with negative numbers, and 0 still tells me what is the part in M. Good. So now this has the dual counterpart to universal R matrices. We have now universal R forms, and they will be given in terms of this proposition. It says if you start with a co-algebra H, then your category of right H comodules is braided monoidal if and only if H is a co-quasi-triangular bialgebra, which is just by definition a bialgebra with a convolution invertible map R, now from H tensor H to K, which we call the universal R form, satisfying 3 axioms. That, okay, I'm going over this quickly because, okay, this can be more easily written in terms of the convolution product. So I just recall you that the convolution inverse of R is a K linear map R minus 1, still from H tensor H to K, such that this equation is satisfied. And this just means it's the inverse, via the or for the convolution product. So if you write everything with the convolution product that I write as this star, then the 3 axioms of the universal R form write like R convolution product with the product equals the opposite product convolution product with R. And similar way here, if I compose the product on one entry of R, then this gives me 2 copies of R. So it's really the dual definition that we have seen for the quasi-triangular bialgebras. Furthermore, I call R co-triangular if the convolution inverse is given by R opposite, so the flipped R.
Wait. So here, this inverse means convolution inverse.
Yes. So here, recall that the convolution inverse, so here I write R minus 1. I want to use the same language as for the quasi-triangular. Just here, everything is dual. I still write R.
Maybe it would be safer to add R star minus 1.
Yeah, you can do that, even though I would say it's rather standard that if it's clear that this is the context, you can write R minus 1. Okay. Whoop. Good. So here I just write for the category of right H comodules, and given a co-quasi-triangular bialgebra, what is the coaction on the tensor product and what is the braiding? So the coaction is, of course, just use the coactions you have on M and N, and then the product on H. And the braiding is just, again, use the coactions you have on M and M, then apply the universal R form, and afterwards the flip. So this gives you the braiding on the category of right H comodules.
I see, and now for a second you shifted and
Yeah,
but it's okay.
I was also like very worried that something horrible might happen, but it's fine. Okay, so in this setting, it's very natural to understand or to try to figure out what are the corresponding infinitesimal R forms. So this will be just the algebraic structure for a co-quasi-triangular bialgebra, such that the category of right H comodules is a pre-Cartier braided category. And so it's, you can figure out it's K linear map pi from H tensor H to K. That convolution commutes with the product and has these two axioms that look very similar to the dual one, just now written in terms of the convolution product. And again, we call this still a Pre-Cartier co-quasi-triangular. So, and if our convolution chi equals chi of convolution R, we call it Cartier. Good. And all statements that we have seen in the quasi-triangular case also work in the co-quasi-triangular case. So I'm not going to bore you with the details, but all of these things with Hochschild also work here now in the dual fashion. Okay, so in the last 24 minutes, let's do something more interesting. And okay, we mentioned these examples of quantum, so Q deformations of matrix groups. So let's have a look at one of them here. Take some complex number, it shouldn't be 0, Q. And then the quantum 2x2 matrices, they are the free algebra generated by alpha, beta, gamma, delta, modulo the Manin relations that we have seen in one of the previous slides. This has a bialgebra structure simply by the matrix co-multiplication and this co-unit here. And you can show that there's a co-quasi-triangular structure given on generators like this. What we showed that for this co-quasi-triangular bialgebra, we can find a non-trivial infinitesimal R form that we write as partial Q, tensor partial Q. I'm going to tell you what this partial Q is in a second. And this makes this bialgebra even into a Cartier bialgebra. So we have this extra commutativity of R and chi. So partial Q is defined in the following way. So I define it on homogeneous elements as the degree of the element times epsilon of the element.
And degree.
Yeah, so what is the definition of the degree?
Yes.
I mean, this is
The greatest structure on this.
so this you can see. So you just count how many generators.
So all these generators are of degree 1.
Exactly. Okay. Exactly. And you see that with these relations, you always
They are
stay
quadratic, yes.
inside.
And you have some basis theorem, right? Which allows you
Use this
to verify that it makes sense. Yeah.
But this is very well known. This is nothing.
Even without very no? These are homogeneous relations.
Right. And so you can show that this partial Q is kind of interesting because, okay, it satisfies a Leibniz rule in this way, and it's central in this sense. So it's kind of, and using those properties, you can easily show that chi is an infinitesimal R form for this quantum 2x2 matrices. So this is fine, but what would be more interesting is GLQ2 and SLQ2. Can we say something about those? So these we get from the quantum 2x2 matrices by quotienting in a certain way. And for this, we need the quantum determinant, which is defined here. And for GLQ2, I extend by a generator theta that I want to be the inverse of the quantum determinant. And for SLQ2, I set that Q equal 1. It is known that GLQ2 and SLQ2 are co-quasi-triangular Hopf algebras with bialgebra structure in R coming from the 2x2 matrices. So for GLQ2, what we do is we extend the partial Q in this way. So on MQ2, it's just the usual partial Q. But if we have some theta to the power n, we set it to be -2n. And you have to show that this extension is well defined, and it is.
It is strange.
Maybe.
Because the quantum determinant is quadratic. So if you divide by this relation, it means that theta should be of degree minus 2.
Correct. Yes.
So, but this delta partial bar should be this derivation. But it's degree. Yes, but it's degree times this element. So this should be minus 2n times theta to the power n. Aha. Otherwise,
in this case, it's really just minus 2n.
so this lifting of this to this partial hat. What is this algebraic? It's not a derivation. What is it?
For the moment, just a linear map.
Linear map.
Nothing else, yeah.
Aha.
And you have a basis, so you can write this linear map on the basis, really no problem. And you can show that chi now defined as the partial Q hat is still co-quasi, so it is an infinitesimal R form for this co-quasi triangular pop algebra.
But how do you prove that this chi satisfies this equation if this partial hat is only a linear map?
It's a computation. I mean, you can write
Computation.
It's not really difficult.
Not using the fact that this partial bar is a derivation.
You use it, that this is the case on MQ2, and then you have to say what is happening if the theta appears, yeah?
Okay.
And it's kind of, so it's also killing the thetas, yeah? So you can say that you will get something that is an MQ. But, okay. Just saying, so this was very nice to find it. The next question was, okay, what is happening for SLQ2? We tried to see, does this chi descend to the quotient of SLQ2? And it does not. You can show that, for example, if you plug in the determinant here, you get something that's non-zero, while if you plug in 1, it has to be 0. So this doesn't work. You cannot use chi on the quotient of SLQ2. And it's...
Yeah, so it is expected because this partial bar, partial hat is not a derivation. So there's no reason to
right. We
compatible with the relation.
We just wanted to check, and it doesn't work. And it's it is even worse. We could show that there's actually no non-trivial infinitesimal R form on SLQ2. So only chi equals 0 works. Yes, so SLQ2 is a bit cursed. We are more optimistic for SLQ3. There's kind of more space, but
even if you, it's strange. Even if you lift it to a derivation, it doesn't work.
We showed that there cannot be any.
Cannot. It's very strong.
Only chi equals 0 works.
Very strong no-go theorem.
Yes. So let's see. We still have some time. So yes, now comes the FRT. Yeah, named after those three gentlemen here. I just walk you through the classical FRT, and then let's talk about the modified one that gives us a way to get the chi's. Yeah. So the theorem tells us that if you have a braided vector space, this gives you a co-quasi-triangular Bialgebras. It gives you a way to get this. So a braided vector space is just a vector space with an invertible solution C that is an endomorphism of V tensor V. So this endomorphism has to satisfy the braid equation here. So this is an equation on the triple tensor product of V into the triple tensor product. And it just says if I apply C to the first two, then this next C to the last two, and so on. Okay, this has to be satisfied. That's a braided vector space. Okay, in the finite dimensional case, we choose a basis of V, let's call it V1 to Vn, and we take n squared generators capital T with indices I and J, and look at the corresponding free algebra that we call F. This turns out to be even a Bialgebras if we take the matrix coproduct. So here just the finite sum over K is understood, and the co-unit being the Kronecker delta. Good, so let's take the coefficients of C, and using those, we define a two-sided ideal in the free algebra. So this we call IC, and this is generated in this way. So we have two T's, and the C with sum over m and n, in this case on the left, in this case on the right. Yeah. Very well. You do this and you take a look at the quotient algebra. And this we call AC. It turns out that the quotient algebra is even a bialgebra, so the coproduct and co-unit descend to this quotient.
Sorry, is it the same as to take this monoidal category generated by V and then this forgetful factor to vector spaces, and then you obtain that this corresponds by this Tanaka reconstruction
Yes.
to some bialgebra?
Yes.
Is it the same?
I'm not sure it's the same, but it's definitely related. I think maybe Tanaka-Klein is more general, and this is a special case that works for finite dimensional vector spaces. But it's almost the same thing, I would say.
Okay.
Okay. Okay. We even get a left coaction of this bialgebra AC on the vector space V, but it's not important. And the theorem of FRT tells us that for each finite dimensional braided vector space, you can find a co-quasi-triangular structure that is even fixed if you say on generators, it is given by the coefficients of C with a certain subtle index flip here that I'm not going to talk about. And this is in fact how you get most of the interesting quantum groups. They are, yeah, you obtain them using this theorem. The question I'm going to answer in the last couple of minutes is, can we find an additional endomorphism T, which gives us an infinitesimal R form on a certain double quotient? And this is what we are going to do. First, okay, what are the relations that T has to satisfy? Okay, for this, we first have to understand very briefly how the proof of FRT goes, and then we are trying to do something similar for chi. So if we take a braided vector space and these generators Tij, we take the bialgebra, the free bialgebra, we create an R. This is for the moment just a linear map from the free algebra tangent of free algebra to K, defined on generators in this way. So on the T's, it has to be the coefficients of C. And if we insert the unit in one of the entries, it has to be epsilon. And then we extend this using this formula. So if we have two generators in one of the entries, we get two copies of R.
So this is a bicharacter in a sense.
I'm not sure if this is what you would call a bicharacter, but so what this means, so the interpretation of this is that this element R satisfies by construction the two hexagon relations of R, which is two of the three axioms that it has to satisfy. And to get the third one, you need this quotient. So this one, the R mu equals mu of R, you only get on the quotient. And this is why you have to do this quotient. Otherwise, this would not be satisfied.
Mm-hmm.
So R is not an R form on the free algebra, but only on the quotient. This is the take-home message. So what we are going to do is, take a braided vector space, take the corresponding R on the free algebra. Now take an endomorphism T of V tensor V. For the moment, just arbitrary, and the coefficients we call T, K, L, I, J. Okay, on the free algebra, we define our chi on generators like this, coefficient of T, and if you insert a unit, it has to vanish. And extend this with this rather complicated looking formula. You have to show that this makes sense, that it's actually well defined, and this was part of the job that we did. This gives you really a map on the free algebra. And the reason why we extended chi in this way is that then this map chi, by definition, satisfies two of the three axioms. Yeah, this is just how it is. And now we also want to impose this commutativity with the product by going to a certain double quotient. Now we want to quotient the relations that are needed for this last axiom to be satisfied, but also in a way that does not spoil the properties of R. So we have to respect also R. This is just motivation.
I don't understand this commutation.
Yes. So this is one of the axioms of chi, is that it has to commute with the product.
It's not a relation between chi and chi op.
No. This was
This is okay.
This is really part of the definition of a Pre-Cartier structure for the co-quasi-triangular
So can you remind me how we got F out of V?
How we get F out of V? Yes, absolutely. So you take a basis of V. Let's say it's of dimension capital N. Then you take N squared generators. That you call capital T by J. Yeah. And you take the free algebra. Okay, now I have to go back a lot, but just the free algebra generated here.
Okay, you wrote it here. Sorry.
Yeah, it's a bit technical. It's just that I don't have much time, so
We have 10 minutes.
I have 10. Okay, so let's see if you can understand the at least this FRT. So okay, how to get this double quotient in a way that everything makes sense, and this will be written here. So let's fix a finite dimensional braided vector space, and we know that by the usual FRT we have this co-quasi-triangular bialgebra ACR. Take any endomorphism T with coefficients T, K, L, and now take the two-sided ideal IT in AC generated in this way, which is just the way we got the quotient AC, where here we had the small c, not the small t. So we just take this other endomorphism and we take the corresponding quotient algebra.
And these with subscripts are basis elements.
Yes, this was written in one of the previous slides. Yeah, exactly. So it's just telling what is it doing on a basis.
And this quotient, sorry. This is
quotient algebra. Okay, then we can show in a lemma this quotient algebra is actually a bialgebra. This is good. Moreover, R descends to a co-quasi-triangular structure on this double quotient if and only if those two relations are satisfied. Well, okay. It's not difficult to show. I mean, basically we're doing linear algebra. Yeah. Furthermore, we have seen how to get this map chi on the free algebra. The statement now is that this descends to a map on the double quotient if and only if those two equations here are satisfied. They look a bit more complicated, but okay, it's simply, you see this happens if and only if those are satisfied. Huh? So those sets of equations are not independent. Yeah. So we tried to compact them in the nicest possible way. And what we got is this 1 and 2. And this is what we call an infinitesimally braided vector space. That's the new definition. So it's just a finite dimensional braided vector space with an extra endomorphism T such that 1 and 2 are satisfied. Looks pretty horrible, but in some cases we can understand this pretty well. For example, if C is simply the tensor flip, then 1 is automatic, while 2 gives you what is called the infinitesimal pure braid relations that were studied by Kono.
Why is it pure braid?
Yeah. You have to ask Kono. It's something that is known in the literature. Yeah, just saying this kind of appears naturally, which was nice. Yeah?
So pure braid means being in the kernel of the homomorphic from the braid group to
permutation.
Okay,
Yeah, that's the answer, yes. So you're going to have to have convex and as much.
Okay, it's a good option. Yeah, I see. Furthermore, for every braided vector space, you can solve this by taking as T a multiple of the identity. This is always an easy way to solve 1 and 2. Let's have something slightly more non-trivial. if you take a braided vector space of diagonal type, which means that your C is the flip and you multiply by a non-zero element, this gives you a solution of the braid relations. And for those guys, we classified all possible solutions of 1 and 2. You can show, for example, what works. You simply take T maps VI to VI and you multiply by something. Can be 0, can be non-zero, we don't care. This is one way how to solve 1 and 2. We have even a more complicated classification of all possible ways. I didn't write it here because it's a bit long, but so this we can solve at least for the diagonal type. We can classify it.
How big is this exhaustive family of solutions? How many parameters?
I have to look it up. The theorem is like half a page. Yeah, it's a bit complicated, but
How many parameters?
There are some. Yeah,
depending on the dimension of V.
I have to look it up. I don't know it by heart. Yeah. Okay, and so this is just recalling what we did. So if you take an infinitesimally braided vector space, so as you've seen, when it's 1 and 2 are satisfied, you take first of all the quotient that you get by FRT. You take the second quotient coming by the that you get from the coefficients of T in this way. And we showed that for any such infinitesimally braided vector space, we find an infinitesimal R form on the double quotient that is fixed on generators to be the coefficients of T, such that this is a pre-Cartier quasi-triangular bialgebra. So this is nice. Furthermore, since we have seen that for any braided vector space, we can take simply multiples of the identity. This gives us non-trivial infinitesimal R forms for any FRT bialgebra. And the explicit formula is written like this. It's basically some multiples of the quotient. And the example of MQ2 that we have seen is of this type.
This is nice.
This is how we found it, yeah. And
so Manin didn't know it.
That's something that we did, yeah. So maybe Manin knew it, but I didn't find a paper of Manin saying this. But yeah, it's
nice.
And we've also a converse statement that tells so how to get infinitesimally braided vector spaces. You take a pre-Cartier quasi-triangular bialgebra, HR chi, and any left H comodulo V. Then you can make V into such a braided vector space by defining C in terms of R and the coaction, and T in terms of chi and the coaction. So it's really both ways work. So now, since I'm running out of time, there is a Tanaka-Krein theorem that we also have, but I think I have to skip this. I can just very briefly tell you the usual Tanaka-Krein. So we'll just show you the theorem that says that any braided monoidal category can be, in a nice situation, mainly if you have a strong monoidal functor to vector spaces, it can be understood as coming from, as factoring through the finite dimensional comodules of a co-quasi-triangular bialgebra in this way. And we proved that the same thing also holds in the Pre-Cartier, yes. So, I mean, here I have sketched the proof. It's kind of interesting how to get H, to reconstruct H, but we don't have time for this. Just here's the theorem that everything works well in the Pre-Cartier setting. And then in the last minute or 2 minutes that I have, I just want to tell you very briefly what I'm having in mind for the future. So at least two.
So back to the future.
Back to the future, exactly. So what we were mentioning in the first minutes actually was this deformation problem that arises naturally. We saw that chi was motivated kind of from formal power series and then reading the properties of this R tilde in first order. So what about the converse? So let's say given any quasi-triangular, any Pre-Cartier quasi-triangular bialgebra can be defined an R tilde on formal power series such that this formula holds. So such that R tilde quantizes chi. We can do this for some toy models. For example, for Sweeter's Kopfalgebra, the exponential works pretty well. And for the Redford Kopfalgebras, this also works. But for the general question, I have no clue how to solve it. We think it should be related to what is called Gerstenhaber-Schack cohomology. And it is definitely related to Ettinger-Kashtan quantization of quasi-triangular Lie bialgebras, because this is what you get if you set R to be 1 tensor 1 and chi coming from a classical R matrix. Then this question is Ettinger-Kashtan, which is a non-trivial theorem. So the expectation is that this question might be very difficult, but we are trying. And the second project that I'm going to that I would like to mention is, so I said that these properties of chi look a bit like a Leibniz rule. And so this is now the motivation. If you fix one of the entries of chi, you can write a Leibniz rule for this chi A that really looks like a vector field acting on a product of functions, where the second term is a braided one. Yeah, so chi A would like to act on C, but it has to pass through B. This is why you get a braided term here. Yeah? And what we showed is that this actually gives you a vector field calculus, so something dual to a first order differential calculus. And for this one, what we are trying to do is understand a bit what are connections and curvature, maybe study metrics, Levi-Civita connections, but this is far in the future. It's just part of the motivation why I find these guys interesting. And here are just some names we cannot read. I know we can read them. So the first line is the starting group, and the second line is people that joined us recently. So we are an ever-growing force working on these questions. And if you're also interested, simply talk to me. And
Stefan also. On the next paper.
It's not just one paper, it's like many different, since you can see at least 2 projects here. Yeah. And okay, I end with a list of references, and thank you for the attention.
Thank you very much. Okay, so let's continue with questions. Any questions from this room?
Yes, I have a question. So everything was about this pre-Cartier structure. So you abandoned questions about this symmetrization.
So the symmetrization, I would say, is really something that comes from the example of the universal enveloping algebra. There, this was used.
So for
apart from that,
Bialgebras,
I don't see why to do it. Yeah.
Yes, so it's my impression. No, my impression is that even stating this question is not a good thing, because in this complex, complex, okay, these co-boundaries are not symmetric.
If delta is not, yeah. If the
could you come back to this slide? Yeah. So,
Which slide?
I will tell you, because it's a slide when you have this star.
It's faster with the keyboard, yeah. So if you tell me, then I can find it.
Well, wait. I know that there is a trick. No, maybe this one. Oh, you see?
Yeah.
Now I can see the slides.
Yeah. So go to the page, maybe 20.
If you tell me what it was about, maybe I can help you.
It was about this commutation relation with respect to this convolution.
Okay, so you're talking about the case of comodules. So
Yes, yes.
you have the R forms rather than R matrices.
Yes.
Okay.
So what is the counterpart?
Down. So a lot.
So I forgot the dual version for
More. Let's see more. Continue. Yes, because here
it was closer to
a little bit more because now
20.
Yes, here we have comodules, right? It should be
14, 15, 16, more farther on.
There's quantum SL.
Yeah.
No, sorry, you have to go back. It was before the SL, before. Go back. I should bring that handout next time, then it's much easier. Back.
Yes.
Back. Further. Yes, here. I think here is a good.
Okay.
So maybe I click and then you can.
So this is for
This is the R matrix. So this, sorry,
Yes.
R form, yeah?
Yeah.
You want to see chi in this?
Yes.
This is now.
How this condition for star commutation comes from these relations?
So
Because I cannot see
here, we are here, yeah?
an infinitesimal form. Yes. So how this commutation comes from taking the infinitesimal part of these previous relations? Because
okay. So I tell you, so in the dual picture, when we have the R matrices, this axiom corresponded to chi commuting with delta. While here now it's
chi commuting with delta.
We had chi times the coproduct equals the coproduct times chi. And now we have the since this is
now we have U, which is multiplication, which is dual to multiplication,
and we have the convolution product.
Okay, now I see. Okay.
And you can show it's really the correct thing if you want the category of comodules to be pre-Cartier. This is exactly what you have to ask for this operation T to be a morphism.
Okay. Now, can you come back to this slide with this partial hat extension?
This should be now afterwards. So here is quantum 2x2 matrices.
Of course, you have this no-go theorem.
So this is the partial, yeah, but you want to see the partial hat.
Partial hat, yes.
Should be on the next slide. Next time I really bring the handout.
Yes. So I would expect that this partial hat should be a derivative in this localized algebra, because you are inverting a central element. So if you are inverting something of degree 2, you obtain something of degree -2. Okay, and you have this grading, then derivations extend in a usual way. And so I'm surprised that if you apply this partial to this relation, you obtain non-zero. It should be 0.
I mean, it's a
alpha is
computation,
but why? Because it's chi alpha tensor det. Why are you focused on this element?
I just want to say that it does not descend the quotient, and for this I have to say that the relation here is not satisfied or not. Okay, chi does not vanish on this relation here.
So alpha is what is alpha? It's a number. Number. It's a number.
No. Sorry, here alpha is one of the generators. So we have that.
Yes.
By 2 matrices, the alpha, beta, gamma, delta.
So it's the
first one, yeah.
Yeah. So this is strange because this relation is not homogeneous. Because it should be something quadratic.
Homogeneous in every entry. So I have to show that if I have something here.
I see. I see. So even if you extend this partial to partial hat, which is a derivative,
probably I would have to check, but I think so.
it still will not work.
So here we showed it's not working in this way, and we showed something even more crucial. It cannot be done by any chi that is different from 0.
Yeah, but this doesn't work for SLQ2. But why? Because GLQ2 is like adding the inverse of that Q.
Absolutely, that is written here. Yeah.
Yeah. So it's like inverting theta. So if chi is something like by derivation, okay, this should be compatible with homogeneous relations.
I don't know what to say. We showed that it is not. Yeah.
So this is very interesting.
Thank you.
Yeah.
So
It's not a cheap consequence of something. Yeah. So this proposition should be a theorem because it's a really strong no-go theorem.
and it also tells you something about,
Of course, the proof is very
condensation. This quantization question. This also means that if I want to quantize these R that I have on SLQ2, I cannot do this in a non-trivial way in first order, because the first order would be some chi that we see here we don't have.
Yeah, but SLQ2 is a different question, because look, in this SLQ2, you have this theta, which is of degree -2, equaled with a number 1,
Yeah.
which is of degree 0.
Yeah, so this is
So this spoils this homogeneity. So I would even not ask this question about SLQ2, but I would but you should prove some analogical no-go theorem for GLQ2.
But we have one, so the no-go theorem will not hold.
Yeah. Have a go theorem.
We have a go theorem. Yes?
Yeah, but still this lifting, this linear lifting of this partial hat,
We don't like it.
it's something strange. I would be happy to see the proof of this proposition, because if this is not a by derivation, so how you can check compatibility with these relations? It's a by this must be by a miracle. Maybe it is so, yes, but it's not expected.
I think also the way how
So this also should be a theorem, because it's not expected.
yeah, so I think the way how we proved it is we try to pin down first of all if there is one. So let's say just by assumption, if we have one, what would this chi have to satisfy? And then something that comes out is that that on this theta something like this has to happen. Yeah, and then we could guess that okay, maybe this is the correct chi, and then we couldn't verify it. But it was really a consequence of playing with this Bialgebra.
It's very strange.
I mean,
It's very strange that this linear lifting can work to create such a chi. So if it is so it is a real miracle.
something that I really, so I was baffled a bit is that, so I think these questions are rather natural, really just asking what is the first order information of an R matrix.
Question is natural,
But means that no one did it. So yeah, we're really,
yeah, but this lifting is for sure is not natural. Because you have on the table this lifting making it a derivation on this. It's like multiplying the right-hand side by theta to the power n. This I would understand. This for me is mysterious. Maybe it works, but by a sheer miracle.
I will send you the and
I would be very.
you can have a look at the proof. I'm
grateful. Yes, yes.
Spelled out in full detail. So I think
Yes, this calculation must be interesting.
Okay, any questions from Zoom? Adam, go ahead.
Yes, so in your references, you had some paper which had the word bosonization. in the title. Could you say a few things about it? What does it
Yes.
mean?
So you can go there. I think this is probably the one by Heckenberger and Vendramin.
Probably, yes. Yeah.
This one here, yeah. So what they're doing, so they talk about infinitesimal braidings for symmetric categories. Yeah. So here the braiding squares to 1. And in this case, it's also easy to have a natural definition of what is a braided Lie algebra and a braided Lie co-algebra. I would like to stress that this question is much harder if you are in the non-symmetric case. So for a general braided monoidal category, it's not really clear what a braided Lie algebra or braided Lie co-algebra should be. However, in the setting of this paper, that is with the symmetric categories, you can do this. And then using the chi, you can build what they call a curved Lie bi-algebra. And they use bosonization
In the sense of Majid.
in the sense of Majid, yes. So yes, this is the picture. And yeah, please.
So this is called bosonization since we deal with something which is symmetric, yes?
Yes, exactly.
Okay, thank you.
Anybody else from Zoom? I don't see any questions, any hands raised. So let me finish with one very simple question. What is your take-home message? What it is you consider most important and you would like us to remember?
So what I would like you to like Hauptsatz, the Hauptsatz. So the first order deformation of a structure can lead to unexpected theorems that are interesting. And we started developing this theory for braidings, first order deformation of braidings, and they led to some very interesting theorems. And we are just starting, so there are many questions to be answered.
Which theorem I should point at?
Which theorem you should point at? I like the one about the Hochschild co-cycle and the Hochschild co-boundary. That's something that I...
Which page?
Oh, it's maybe here if you go. So no, it's you have to go. No, this is Tanaka Klein that I didn't even mention. So
okay,
it was one of the first pages. So if you go here, maybe. Yes, let's see. Yeah. Okay, stop. And go down, because this is still Hopf algebra. Down, 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 down. This is examples. Maybe after this one it should be there. Yes. So
I haven't.
Yeah. So we'll look at this one. Yeah. So for example, here that you ask something about braidings and out of nothing you get some Hochschild co-cycle that was not expected. Yeah. And then okay, we could even show that if you ask a little bit more, you get boundaries. So this I found quite.
Okay, and this is the natural Hochschild complex given by the component. Okay, so let us hang up.
Can I ask one question? Sorry. Could you come back to this infinitesimal Tanaka reconstruction?
Okay, sure, I can.
Okay. So your neutralizing functor is to vector spaces?
Yes.
Why not vectors, free modules or projective modules over power series? I would expect that
for the power series. So this thing you have to do when you also think of information theory. Then I think this is the correct forgetful functor to look at. Yeah, but
or modules over dual numbers, let's say.
Yes, but so here yes, we are using this correspondence of braidings with our matrices, and this uses the functor to vector spaces. If you want to do this deformation story that you, for example, do in order to get the Drinfeld Jimbo quantum groups. You have to go to formal power series, but this we can only do in some very special cases like universal enveloping algebra. As I showed you, this future project would be quantizing and understanding this better. For this question, we have to go to formal power series, but this is not needed in order to talk about co-cycles and so on.
Yes, but no. Okay, if I'm interested only in the first order deformation, it is enough to speak about dual numbers. So this is not a vector. This is not a field. It's a finite dimensional algebra. Okay, and then you could consider some finite generated projective modules over dual numbers. So this is the natural counter image counter domain of this neutralizing functor.
Yes, and we are thinking about this for this deformation question, because there I think we have to do this, yeah. But
the first order deformation.
For the first order,
so this should be this should correspond precisely to your infinitesimal question.
Okay, so this I don't see. Why? Because for me it was fine to go to vector spaces. There,
vector space.
Tanaka-Klein works very well.
Okay.
Okay, so can we now?
Yes.
Thank you so much. Let me stop recording.